Well, congratulations if you made it this far. You're on the last video of this series of tutorials. And in this one, we're going to bring everything together to look at a complex ternary phase diagram and see if we can read crystallization paths and interpret all of the information that's on it. And the diagram that we're going to look at is shown to my left. It's the ternary magnesium oxide alumina silica system. So we're going to go through this system, and after this, I think you'll be able to handle everything. I'd be interested if you have any comments on the videos, feel free to post them. Good luck. The MgO-Al₂O3-SiO2 ternary system has been studied for many years. Indeed, the original phase diagram shown here was determined back in 1964 through an extensive set of experimental studies, and there is a wealth of information on this diagram. Compositions within this system are important for many reasons. They're important to geologists looking at mineralogical systems, and also many of the compounds in the system have important applications as high-temperature ceramics. For example, as structural ceramics in kilns and ovens. Also, compositions in this system form transparent glass ceramics. And as I mentioned, from a geologist's point of view, they constitute many of the lower mantle minerals. Understanding the melting behavior and crystallization paths in this system, therefore, are very important. It's also a great test system to see if we can apply our knowledge from the previous videos to read crystallization paths from a liquidus projection. Many months or years of studies led to the experimental determination of this system and a detailed characterization of the phase stability and melting temperatures. Our objectives here are to read and interpret all of the information on this diagram, and then to use the liquidus projection to track some solidification paths. One thing just in passing here, I would note the compositions in this diagram shown, the percentages are actually mass percent or weight percent rather than mole percent. However, that does not interfere with how we are going to read and interpret the diagram. So here I've redrawn the diagram, and the first thing to do is to make sure that we understand the notation and all of the various compounds that are represented in the system. And in blue here you see part of the diagram where it's a little bit congested is blown up. We'll come to that section later. First, with respect to notation, the intermediate phases are shown here in red, and there's a number of them. Along the MgO-SiO2 binary there are two compounds, MgO-SiO2 or MgSiO3, mineral name protoenstatite, and phosphorite olivine is the mineral name of Mg2SiO4, which is represented here as 2MgO.SiO2. Both of these are essentially line compounds and show no solid solubility either side. Along the MgO-Al2O3 binary there's a well-known phase MgAl2O4, represented here just through a formula MgO-Al2O3. This is called spinel, and it actually shows a fairly significant amount of solid solution. I'll come back to that notation in a second. The next compound along the SiO2-Al2O3 binary is mullite, 3Al2O3.2-SiO2, and then there are two ternary compounds, one here, 2MgO-2Al2O3-5-SiO2, given the mineral name cordiorite. You may have heard of cordiorite in terms of its applications as a ceramic. And then a phase down here, 4MgO-5Al2O3-2-SiO2, given the mineral name saffirin. I mentioned solid solutions. The notation I'm using here are these hatched lines, indicating that this is the extent of solid solution, in this case between spinel and Al2O3, and there's a significant range. And also around mullite, there's also a significant range of solid solution, and around this compound in the middle, cordiorite. The Al-Khamadi lines, the solid state compatibility triangles and lines, are shown here through these hatched black lines. And this breaks the triangle down into a subset of three-phase compatible subtriangles, two-phase regions, etc. Finally, with respect to the liquidus melting, we'll see two types of information. First of all, liquidus isotherms, in other words, isotherms that show the temperature at which crystallization first appears, and they're labeled by their various temperatures. So you see in this case the melting temperatures get very high, 2800 C for example for MgO itself. And then the liquidus projections, projecting eutectic or peritectic valleys, are shown in dark black as before, with the arrows indicating the direction of decreasing temperature. As we've mentioned in the previous videos, the first thing we should do for any ternary is identify the primary phase fields. And actually in the experimental diagram that I showed originally, these were already labeled. Let's make sure we can identify those ourselves. Beginning in the lower left, here within the various liquidus projections, this is the primary phase field of MgO. Again, any overall composition within this region, the first phase to crystallize would be MgO. Working our way up, then if we look at this liquidus coming out of the MgO-SiO2 boundary, you should see that it's lying between these two solids, MgO and 2-MgO-SiO2, so this is in fact a eutectic, and so the primary phase field to the right of it is 2-MgO.SiO2, shown here. Now let's look at this liquidus coming out of the binary system at 1557, if you can see that. It's tempting to say this may be a eutectic, but in fact it's not, because we see between these two compounds, 2-MgO-SiO2 and MgO-SiO2, there isn't a liquidus emanating from between the two of them. So this one is not a eutectic, it's a peritectic. And it must be involving these two compounds. It's outside the two compositions. So to the left of the liquidus is the primary phase field we already identified, 2-MgO-SiO2, and therefore above it, this must be the primary phase field of MgO.SiO2. Then we come to this liquidus coming out of the system at 1543. This is a eutectic between SiO2 and MgO-SiO2, and so this primary phase field here is SiO2. You notice there is another liquidus line here with two arrows pointing towards each other. This is something that we haven't really gotten into, but it's related to liquid-liquid immiscibility, and we'll just put that aside. Continuing to work our way along binaries, down at the lower right here, this is the primary phase field of Al2O3. Now working along the Al2O3 MgO binary, this whole area here must be the primary phase field of MgO-Al2O3, spinel. Now we'll come up the Al2O3-SiO2 binary. We already know this region's Al2O3, so up here, just tracking back to this liquidus in the binary, looks like it's a eutectic between 3Al2O3.2-SiO2 and Al2O3 itself, and indeed that is the primary phase field in this region of mullite. So we've successfully identified the primary phase fields of all the binaries. Now there's a couple remaining in the middle of the system. This is actually the primary phase field of 2-MgO, 2Al2O3, 5-SiO2, and we see it lies outside the composition of that pure solid, but within the region of the solid solution. And then we've got a little region in the middle, which is the part that I've blown up outside to the right here, this primary phase field within this triangle. It's actually the primary phase field of safran, and here's the formula of it. So in this case, the primary phase field of this compound is significantly removed from the composition of the pure solid itself. And so we're going to have to be careful when we look at crystallization paths and bear that in mind. Bringing all of that together, here are all the different primary phase fields in the system with their various labelings. Now we'll select a couple of compositions and go through a crystallization path. The first one we'll pick in this lower right hand corner here. Here I've got it just blinking away so we can see it. That's what we want to focus on. I think it would help if we enlarge this region of the diagram, because that's where all the action is going to be, just to make sure everything is legible. So here we are, here's our composition number 1, and we want to track what happens as it's cooled from high temperature. And given that we've got all of these isotherms with the temperatures labelled, we can be pretty quantitative about this. Well, the first thing, if you remember, is to identify the final product. What will we have after all is said and done and we've cooled down to room temperature? So we want to ignore all of the information except that pertains to the solid state stabilities. In other words, we want to look at the Alcomadi lines. Now we've got to be careful here, because with the solid solutions there's a lot of lines, some of which constitute two-phase regions. Let's put those aside and let's just focus on composition number 1. And we see it lies in this triangle that extends from 3Al2O₃-SiO2 down to a composition in this spinel solid solution at another corner, and Al₂O3 itself. So using the Alcomadi lines, I've put in the triangle and shown the final compositions in black, and I'm just doing that from reading those solid state compatibilities that were experimentally determined and put on the diagram. So just pulling that off and blowing it up on the left, in the end we're going to have 3 phases, one of which will be a solid solution of malite at the end of this solid solution region here, shown at the end of my mouse. It will coexist with a spinel solid solution, composition designated here within about the middle of that solid solution region, with Al₂O3, which is a line compound. And we could quantify the relative amounts of each using the lever rule. So that's the final product. How do we get there? First thing we want to do is to look at what is the first phase to form, the primary phase, and to do that we just need the primary phase field, and we've already labelled that and it's clearly Al₂O3. So let's shade that in. So the first phase to crystallize here will be Al₂O3. Given the Liquidus isotherms have been provided for us on this phase diagram, we can specify exactly what temperature that will happen. So here, looking at these blue isotherms, let's see, this is 1800, so this one's 1900 C. We see our composition lies between the two isotherms, it's closer to the 1900. So the crystallization of Al₂O3 will occur at roughly 1880 C. So we're all liquid until 1880. Now we know as Al₂O3 crystallizes out of the liquid composition itself will move in the opposite direction over the liquidus surface to lower temperatures. And so here's my straight line path away from Al₂O3, showing the direction of the liquid headed towards this valley, this liquidus shown on the diagram. We can quantify the temperature at which the liquid reaches this 3-phase valley using the isotherms. This is 1700 C, this is 1800 C, so at about 1725 C we will reach that 3-phase valley. And when we do, we're going to start to form a second solid phase whose primary phase field is on the other side of the liquidus, i.e. 3Al₂O3-SiO2. Well, now we have a 3-phase equilibrium. We use tie triangles. So let's add the first tie triangle as the liquid just arrives at this valley. So here's my liquid, here's the composition of one solid within this solid solution region, and here's my Al₂O3. We see the liquid composition lies outside both of the solids. And so using our rule left plus right in equilibrium with the middle, we can see that at this point this is a peritectic valley. And so we have liquid plus Al2O3 in equilibrium with, or forming, this mullite solid solution. As we keep cooling, the liquidus is constrained to the valley. It'll move down. And the issue is going to be, does it get to this 1578 ternary invariant reaction? So let's just show the path of the liquid. I'm moving down. Let's put it at this 1578 invariant by using another tie triangle. So this is my tie triangle now where the liquid is at 1578. These are the two coexisting phases. Where's my overall composition lying? It's in the middle of the triangle. And so clearly I have liquid remaining that must further cool and undergo more reactions to fully crystallize. Next is to identify what is this reaction at 1578. We're going to see it's actually a peritectic, and let's go to the next slide to focus on that. So we're at 1578, liquid still remains, and this in fact is a 2,2 ternary peritectic, and we're going to start forming MgO-Al2O3, which is the other primary phase field surrounding this invariant. So let's shade that in. Let's just pull this section off for a second so we can make sure that we're all on the same page in terms of identifying this peritectic reaction. Okay, we have two liquidus valleys coming in, it's these two lines, and we can see one coming out, one exiting from the reaction. And we know from our previous videos, in this case, it's a 2,2 because it's liquid plus the primary phase that lies between the two liquidus valleys coming into the reaction. So liquid plus Al2O3 in equilibrium with, on the other side, the two exiting primary phases, MgO-Al2O3 and 3Al2O3-SiO2, both of which are solid solutions. So this is my 2,2 ternary peritectic. When four phases coexist, we use a trapezium. So let's get rid of the tie triangle, and now in brown I've highlighted the compositions of the four phases that coexist at this peritectic. The liquid, the spinel solid solution that is now forming as a result of that peritectic reaction, Al2O3, and the mullite that we had going into it. So again, let's pull that off the diagram, show it on the left. Here's the four phases coexisting. The next thing we should ascertain is one or the other of these two species on the left, the liquid or Al2O3, are going to be consumed. Which one? We look at the subtriangles, and we see our overall composition lies within this subtriangle formed by the three solids. If it was in here on the other side, then we'd still have liquid remaining, but it's not, and so liquid is consumed. That means we're finished. The crystallization is completed at 1578, and our final phase assemblage is the one we showed before, these three phases here. And here's a summary of the path of the liquid during the entire crystallization. The solidification started at 1880, where we formed our primary Al2O3 phase. We went over that liquidus surface, hit the valley, came down the valley, and finished at 1578. Okay, let's take a look at another composition where we'll find the liquidus path is a little bit more tortuous. And the one we'll select is composition number 2. It doesn't look too far away from composition number 1, but we'll see the path is quite different. We're going to blow up this region again so we can see what's going on, and let's go then to the next slide. We'll use the same procedure. First, identify the final product using the Alcamade lines. It's lying in this triangle. Let's just highlight that in blue, And we'll find the final solid state assemblage is a three-phase mixture of a composition of mullite, 3Al2O3.2-SiO2 shown here, 2 MgO-2Al2O3-5-SiO2, so this ternary compound at the top, and then our saffirin compound, just pulling those off. This is my final tie triangle of the solids that will be present after we've fully cooled. We can quantify the amounts using the lever rule. How do we get there? Again, our composition lies in the primary phase field of Al2O3, so that's going to be the first phase to crystallize. And we can see it lies on the 1800 Liquidus isotherm, so that's the temperature at which crystallization will begin. The first part of the crystallization is similar to what we saw before. The liquid will roll down the Al2O3 liquidus surface, moving down in temperature towards the valley that we saw before. The liquid will reach the three-phase valley. We know a third phase must crystallize, and the third phase to do so is the primary phase on the other side of the valley, 3Al2O3-SiO2. Use our tie triangles again, shown here. So at this point, three phases are going to coexist, shown at the corners of the tie triangle. This is the same three-phase equilibrium we had before. Let's just re-identify the equilibrium. Liquid on the left, outside the two solid. So it's liquid plus Al2O3 in equilibrium with the phase in the middle, 3Al2O3.SiO2. So this is that three-phase equilibrium. It's a peritectic. Now the liquid moves down the valley, heads towards that 1578 invariant that was involved in our previous composition. Let's use a tie triangle to highlight the three phases that are present as it just arrives at this temperature. So again, liquid now at 1578, coexisting at this point with just the two phases. The overall composition lies within the triangle. There's definitely liquid remaining, and a significant amount, and so that remaining liquid is going to undergo the invariant reaction. So again, this is our 1578-2,2 ternary peritectic, where we first form MgO-Al2O3 solid. That's the primary phase field on the other side of this peritectic. And just as I did before, I've pulled that invariant reaction out so we can identify it again. So it's liquid plus the phase between the two valleys going in, Al2O3, in equilibrium with the two either side of it as shown. Now we'll use the trapezium, the trapezoid construction. Let's get rid of the tie triangle. Four phases coexist. Compositions shown. I pulled it out on the left side again here. Now our overall composition lies within this subtriangle, not within the subtriangle formed by the three solid phases, but within the subtriangle where the liquid is at one vertex. And so in this case, we will not consume liquid, but we'll consume Al2O3. And so we'll be left with liquid 3Al2O3-SiO2 and MgO-Al2O3. The crystallization must continue. So these are the three phases remaining after the Al2O3 is consumed. So let's replace our trapezoid with a new tie triangle that connects these three phases. The liquid right now just about to leave the 1578 invariant, but that's its composition. And here's the composition of my spinel solid solution and my mullite solid solution. Overall composition lying within the triangle, all three phases present, and still a significant amount of liquid remaining that needs to crystallize. The liquid is going to keep going to lower temperature. It's constrained to this liquidus valley. It's going to move towards the 1482 invariant reaction, which we'll see in a second is in fact a peritectic. So I realize this is very small here, and that's why we've blown this region up on the right, showing that the liquid is going to be moving to this 1482 invariant reaction. Let's just use some arrows to show where it's going. So I'm moving here on the main diagram, coming in here on that blow up. So now let's move the liquid composition there and look at a new triangle. just as it arrives at 1482. So my liquid is at this point, or this point on the blow up. Here's my two solid phases. Is liquid left? Yes, it is. And so we're going to undergo whatever invariant reaction this is. So let's identify this 1482 invariant. You can see on the blow up on the right, we've got one valley coming in and two exiting. If you remember, then this is called a 3-1 peritectic. And in this case, we're going to start forming a new phase, and that will be this sapphire phase whose primary phase field is bounded by this triangle. Let's blow it up on the left just to try and make things clear. So first of all, what is the equilibrium? One valley coming in, so it's liquid plus the two primary phases either side of it, shown here, in equilibrium with the primary phase field that lies between the two exiting valleys. Let's use the trapezoid to connect those four compositions. Here it is, and let's be careful. Liquid, 1482. This is my 3Al2O3-SiO2 solid solution. This is my spinel solid solution. And here is the new phase that's forming. Remember earlier I said for the sapphire compound, as it's called, the primary phase field is far removed from the solid composition itself. It's all the way up here. But this is the solid that we're crystallizing. Let's blow that up on the left. Here's my four phases. Let's look at where the overall composition lies. Which subtriangle? It lies within the liquid 3Al2O3-SiO2 sapphire subtriangle. And so now we see that the fourth phase, in this case that spinel solid solution down here, that's consumed. So we knew we had to run out of one of these three, and in fact it's the MgO-Al2O3 that's consumed. So let's get rid of that phase. It's not involved anymore. I'll remove the primary phase field, and we'll replace the trapezoid by the tie triangle that connects these three remaining phases together. The liquid still at 1482, sapphire and my mullite solid solution, and my overall composition lying within the three. Liquid still remains, so we have to keep going. The issue now, if you look at the right hand side, is it's almost like I've got two destinations here. I could follow the Liquidus valley to the left to the 1453 invariant, or I could follow the valley to the right to the 1460 invariant reaction. Which is the correct one? Well, it must be the 1460, because along this Liquidus valley, the two phases that coexist are sapphire plus whatever primary phase is to the right of it, and that's the one we have, the mullite solid solution. So we go along this direction because we consumed the phase that was to the left of this valley headed down to 1453, which was spinel. And so if we had consumed the other solid phases, we would have trundled down this valley. But because we consumed the spinel, we're headed along the valley towards 1460. Okay, so looking at the tie triangle, these are the three phases remaining, and my choice of Liquidus valley is dictated by the primary phase fields of these two compounds, which must lie either side of it. So we're headed to 1460, the liquid is still cooling, headed in this direction. Now we need to see what this 1460 invariant involves. Alright, well, just as we arrive there, this is my tie triangle. Liquid now has got to 1460. These are my two solid phases. Overall composition lies within the triangle. Liquid still remains. We are going to undergo this 1460 peritectic reaction, and we're going to form yet another new phase. Which phase is it? It'll be the one whose primary phase field lies in this region, 2MgO-2Al2O3-5-SiO2. So let's shade that in. That's going to be the new phase that forms. let's pull that invariant reaction off so we can identify what type of peritectic it is. We've got two valleys coming in and one coming out, and so it's a 2-2 peritectic, liquid plus the primary phase lying between the two incoming valleys, which is our 3Al2O3-SiO2 phase, in equilibrium with, on the other side, the two primary phases that are either side of the exiting valley, which is safran plus 2MgO-2Al2O3-5-SiO2. So use the trapezoid to connect all of those phases together. Liquid at 1460. Here's that new phase that was forming right here, my pointer. These were the two phases that we had going into it. Let's again pull that off on this side here. Now let's see where our overall composition lies, within which subtriangle, to figure out what's consumed. Either liquid or 3Al2O3-SiO2 is consumed. Well, here's the subtriangle. The overall composition lies in a triangle where the liquid is not at the vertex. And so actually it's the liquid that is consumed through this invariant reaction. We're left with three solid phases. The solidification is complete, and we can replace our trapezium by a new tie triangle that connects the three solid phases, and there's our final product. So in this case, the liquid crystallization occurred over a range of temperature from 1800 all the way down to 1460. And this was the path of the Liquidus, where I had the single phase Al2O3 down here, down to the 1578 invariant, to the 1482 invariant, and then to the 1460 invariant. So as I mentioned, the path is a little bit more tortuous than the previous example, but I hope this shows you that if you're careful identifying the phases, using the tie triangles, using the four-phase constructs to look at the coexisting phases for the invariants, you can follow the right path. Well, that's it. That's the end of our ternary phase diagram tutorials. So congratulations. If you've made it all the way through, you are now officially certified to read any complex ternary phase diagram you encounter. Good luck.